This video will explain my Lab 4 for the IE1206 Embedded Electronics course. For this lab, I've built a Schmitt Trigger using components provided in the lab kits. A Schmitt Trigger converts a slow changing input signal, like that of a sine wave that I've used in this lab, into a clean and sharp digital input with no or incredibly limited ambiguity. It does this by setting an upper and lower threshold, which is set using the equation for a voltage divider circuit. When the input rises above this upper threshold, the output switches to high. When the input lowers to below the lower threshold, the output switches to low. We will now look at the Schmitt trigger simulated using LT-Spice. I use LT-Spice as Quoox is not available on the Apple Silicon series of laptops, which is what I have. Nonetheless, the simulations are just as precise. Here, we can see the simulation for the operational amplifier. The voltage source into the non-inverting input over here is a sine wave with an amplitude of 2 volts and a frequency of 1 kilohertz. This is connected to a 1 kilo ohm resistor and feeds into the non-inverting input. To ensure that the op-amp operates in the linear region, we use negative feedback, which means that we feed the output of the op-amp over here into the non-inverting input as well. This output is fed through a 47 kilo ohm resistor. On the inverting input, on the other hand, we simply connect it to ground. The positive and negative supply voltages, that is, plus V supply and minus V supply, are 5 volts and minus 5 volts respectively. 5 volts over here and minus 5 volts over here. While it is labeled 5 volts at the minus point, it is connected through the negative terminal, which means that we end up getting minus 5 volts into the op-amp. In an ideal op-amp, this means that the output voltage is set at either 5 volts or negative 5 volts. But since op-amps come with slew and other internal interferences, as well as interferences within the circuit itself, we get a lower value for the high output and a higher value for the low output. Running the transient simulation as set by the SPICE directive, we get the following graph over here. We set one probe at the sinusoidal voltage source over here and one probe at the output over here. As seen in the unmistakable bright pink, the voltage from the sinusoidal source oscillates between 2 volts and negative 2 volts. The main portion in the Schmitt trigger, however, is in the neon green graph. We can observe multiple things. Firstly, the output is very clearly a square wave, characteristic of that of a digital output. This oscillates between positive 2.8 volts and negative 2.8 volts. Secondly, we can observe the reason for having two resistors within such a large range in resistors. As we saw over here, 1 kilo ohm and 47 kilo ohms. Using the voltage divider formula, we calculate that the upper threshold is plus 0.1 volts and the lower threshold is around negative 0.1 volts. This allows us to cleanly transition between our high and low output voltages, as the range, that is known as the hysteresis range, is very small, only 0.2 volts. Now we will look at the circuit as built on the breadboard. Here we have the circuit on the breadboard. It is connected to the 5 volts power supply of the Arduino, and that is also connected to the ground. The 5 volt power supply is used to generate the negative 5 volts required for the op-amp in pin 11. The 5 volt power supply is also connected to pin 4 for the negative and the positive supply voltages respectively. As we can see, the inverting input is connected directly to the ground and the non-inverting input is connected via the 1 kilo ohm resistor to the operational amplifier. Through the 47 kilo ohm resistor, we connect the output back into the non-inverting input as well. Given that the output of this circuit provided was an inverted output, I used the fact that the TL074 comes with 4 operational amplifiers in it to invert that output and get the correct output. This is done by connecting the previous output to the non-inverting input of the second op-amp and attaching it to a resistor and keeping the same connections as before. We can measure the sinusoidal input and the flattened output using the picoscope, and we will see the results of this in the next bit. So here is the picoscope readings. As you can see, similar to the simulation, we have the sinusoidal input wave, which does not quite reach 2 volts due to interference from all the parts on the negative 5 volt generator and the operational amplifier itself. We can see that the smooth signals peak higher than the sinusoidal wave, as it is dependent on the supply voltage of 5 volts, which is higher than the amplitude of 2 volts. We can also observe that the frequency of the output equals that of the input wave. Otherwise, we can observe that the picoscope measurements match that of our simulation, which is always excellent. Here, I'm triangulating the input, and when we do that, we see that the wave exceeds both thresholds, that is the upper and lower threshold of the Schmitt trigger. Therefore, the Schmitt trigger generates a fairly clean square wave at both crossings. So this was my lab 4, where I built a Schmitt trigger for my circuit using an operational amplifier. Thank you so much. Bye-bye.